Myself Meenakshi Barua. I am starting one very interesting presentation today that is on the topic of mini batch, stochastic gradient descent. So these are all types of gradient descent algorithms, the key backbone of all machine learning algorithms, because whenever we mean that we are training something, we are using gradient descent. So gradient descent algorithm is further of three subtypes. Gradient descent uses the slope or the learning slope, uh, the direction in which the cost increases, as we will see. So we will see that why it is very simple algorithm and how we can. Myself Meenakshi Barua. I am starting one very interesting presentation today that is on the topic of mini batch, stochastic gradient descent. So these are all types of gradient descent algorithms, the key backbone of all machine learning algorithms, because whenever we mean that we are training something, we are using gradient descent. So gradient descent algorithm is further of three subtypes. Gradient descent uses the slope or the learning slope, uh, the direction in which the cost increases, as we will see. So we will see that why it is very simple algorithm and how we can utilize the gradient descent to to back propagate the error we can say, or the changes in the parameters, that is the gradient. Based on the gradient we change the parameters. So what is basically the gradient? Because we to know what is gradient descent, we must know what is gradient, and in turn it turns out that we must know the cost function. So cost function is nothing but to train something, to make the model perform the best, we require that it takes the least cost, means least effort, least least error. It should give the output. Here in terms, it is not effort exactly, it is precise output. To give the precise correct output, what is the error, means what is the error which it deviates from the correct output, that is its cost, that is liability. So uh, actually it is a complete algorithm, gradient descent. So we will definitely find one minimum if correct learning rate is taken for the cost function, that is the positive, how much of the positive slope that we are taking, how at what steps. So if we are here, we should be at the minimum. So if we are taking the gradient too fast, the slope will be like this and its minimum will be incorrect. So in that way, we should take the correct learning rate so that we can follow the cost curve correctly. We can follow the gradient. We can utilize the gradient to to simulate the cost function, to means adjust properly to the cost function. So we should take the learning rate as that. So it is the steepest increase is the gradient. So it is the very smallest step, steepest increase. So we can, in mathematical terms, we can take it as alpha is the learning rate, J is the Jacobian, that is the depends on the actual and goal, that is the y and x. So theta not theta 1 are the parameters, so that is it depends on the parameters, just to show that. And actual what is required, means what is the correct, what is should be, due to which we are unable to reach and due to which we are incurring the cost. So in that sense it is only uh, the final one is the x term, and we are learning, and with the help of learning we are taking the gradient x term. uh, Here it is positive or negative, that is all squared up. So here this is all squared up for the cost function, but after we get it we add or subtract based on the what is the direction. So if the gradient tells that we should increase the parameter, so that the cost reduces, so we can subtract, and if we should increase we will increase the parameter. So Jacobian will be a square term. Square here means that the output will be all added terms will be all positive. So basically square means that it will be a clear cut positive term, so there will be no negative Jacobian. Here I want to mention that the parameters should be mentioned with along with the other things. So mainly theta not theta 1 are the parameters that control the hypothesis, that is the function, that is what we are using for the hypothesizing the um, cost, means the prediction, the output that we are hypothesizing, that this parameter depends this much impact this parameter makes on the output. And output, this is basically output dependent, this is cost function. M is the number of samples, I is iterating over it, parameters are indicated like this, that is standard notation, and J is Jacobian of this. Goal is to minimize this, means cost based, that may lead to increasing one parameter, decreasing, or vice versa, or anything may happen to the parameters, but cost must be minimized. X is the input, uh, that is basically when we use logistic or something, that becomes Z. So that there is something called hinge function that separates the decision plane, means there should be the distance between the parameter and that space and this, so that is a separate different topic entirely, so we are not bothered about the Z. But here X is the training sample, so training sample I is the predicted based on that prediction for the ith sample. So these are the parameters basically. And from the theta, hypothesis theta will be based on the hypothesis, it can be reduced or increased based on the cost function and learning rate. So if the it is learning rate should be gradient is negative, then it will be added for the parameter. So we see from this that for all the parameters the same gradient will be applied, same learning rate will make all the parameters uniformly big or uniformly reduce. So this is the goal we have to minimize this theta, or minimize the Jacobian or the cost function theta naught. Theta 1 will be accordingly, the parameters will be increased or decreased. So here also this same, uh, how much we should learn such that the uh, because the weights are updated, so weights are initially taken as 0, so but these are parameters, so parameters, the learning the gradient, whatever the gradient is, means the that steps, we can take the steps in the positive, in the steps in higher quantity or lesser quantity based on the learning rate. If it is taken and we tend to reduce, so we gradient will be moved towards, the direction will be towards the negative, but the gradient will be uh, positive. This will be a positive term in the direction of decrease. So generally the direction, if gradient is taken in the gradient definition says it is in the increasing sense, so if we are taking in the decreasing sense, then it will be reduced, minus. So that is dependent on the direction. So it is discrepancy between the quantity is the discrepancy between, basically in layman's term, it is the discrepancy between the xi actual and the uh, predicted quantity. So we will not go into that much deep. Iteratively it works by reducing the quantity. If we go in the negative direction, so it will keep on reducing till it reaches the very minimum. So its gradient, so actually gradient descent is only used during back propagation and all, so that is the behind the scene, it is the only thing. Gradient is, if it is taken here, gradient is the slope, as a formal definition is increasing terms. Here as it is said that gradient is the gradient direction of the steepest increase of the cost function. The steepest increase is here, so it is the gradient positive, but here the negative is used for subtracting, uh, move in the opposite direction, increase the current point. So anyhow we have to move in the uh, decreasing direction and take off the direction of the gradient. We have to move opposite to the gradient. Gradient is positive, we have to move negative. So just we have now reached at the first variant of the, at the slide of the first variant. So it has to do with the batch. Batches is batch size, as we know, whenever we do training it is in batches, so it takes just the average of the all the batches and nothing else. So that's just one step of gradient descent in one book. So it is very simple, but here if the training size is too high, then what will we do? How can we average so much of data? Nowadays it is deep learning time, so we have huge volumes of data, so that is the issue. So discrepancy we have to reduce anyhow, so we can go for stochastic. Stochastic is nothing but the same gradient descent with, while taking one example for the training and checking the gradient based on one example, then applying the same gradient for all. So because of taking one example, like here we take one example, feed it to neural network, calculate its gradient, then update the weights. But because of that we get one jittery curve, because one example can be anyone, so fluctuate, and long run the cost will anyhow decrease, but it may skip one local minimum. Here maybe because of taking the wrong example, the minimum may be somewhere hidden anyhow. we are moving to the next variant. Now both the variants we have seen the disadvantages. One skips the minimum, one cannot handle huge volumes of data. So what should we do? We should move to a thing, a variant where we can go to the, like one person is standing at one hill, he wants to move to the bottom of the valley, he should not be stuck in some local value, minima. So what they have, we can do is, we can take mini batches, not entirely batches and not entirely the entire training set. So we can divide the training set into mini batches and use one batch at a time. Like one example we were taking, but this time we will take one batch at a time. So that instead of one example, we will go for one batch. So the same thing will happen, but here we will overcome the, basically we will overcome the missing the local minima because batch will be taken. So in one epoch this all will happen, as you can see the screen. Now here also G3 will result, mini batch descent fluctuates, not like this perfect one batch gradient. So here what happens is this curly braces notation is used for the batch number. So like 10th batch. So for example we have uh, 5000 batches of 1000 training samples each, means it will result in 1, 10, 100,000, 10,000, 100,000, 1 million, 10 million, 50 million records. So and say that each has dimension nx, so there will be, this is used for the sample number. So this much of samples are there, and the similarly the predicted result is this, training sample is this, and based on that the actual result will come, and this is predicted one. So number of sample, this mini batches of 1000 each. So here basically we can do the vectorization. So here the vectorized notation is used. So we can compute the m samples efficiently. Whenever vectorizations always helps to compute it efficiently, and jitteriness will be reduced because of the vectorization, because we have vectorized the, we have one batch and we have vectorized that, and we can efficiently compute it. So here ith sample, and then like in logistic or something, z parameter is used. For l is layer number. So we stop it here because we just wanted to get one overview. So that's it. Thank you very much.